అక్కడ ఫుల్ స్క్రీన్ వస్తుందా?
I think this is fine. Okay.
ఇది పనిచేయదు. ఓకే.
Raghu, పనిచేస్తుందా?
ఇప్పుడు
Yeah, welcome back. Okay. So next talk, afternoon session, we have a talk by Professor Linga Reddy on MM wave radar based sensing for automotive and industrial applications. So I just give a brief, biodata of Professor Linga Reddy. Professor Linga Reddy, received the master's degree in electrical engineering from University of Technology, Delhi, India in 2004, and PhD degree in electrical engineering from Norwegian University of Science and Technology, NTNU, which is the topmost university in Norway. He worked for Texas Instruments in mixed signal circuits design before joining PhD program at NTNU. After finishing his PhD, he worked in radiation imaging for an atmosphere space interaction monitor at the University of Bergen, Norway from 2010 to 2012. At present, he is the group leader of the Autonomous and Cyber Physical System Research Group, and is working as a professor at the University of Agder, Grimstad campus, Norway. He has also co-authored over 100 research publications that have been published in prestigious international journals and standard conferences. His main scientific interests are in cyber physical systems, autonomous systems, and wireless embedded systems. He is the principal and co-principal investigator of many research grants from the Norwegian Research Council. He is a senior member of IEEE. He is also a member of editorial board of various international journals as well as technical program committees of several international conferences. So with this brief, biography of Professor Linga Reddy, now I request Professor Linga Reddy to give his, talk on radar-based sensing. Thank you.
Okay, Krishna, thank you very much. So the talk is based on the millimeter wave radar-based sensing for automotive and industrial applications. I slowly start with very basics so that everyone here who did work earlier already, so that they get some basics. So I basically start with 0 all the way to no. So whoever have very basic mathematics can follow. So first, after the slides, I'll be covering the basics. Then later, I'll be covering 2 important applications. So one is for automotive applications, basically how to set up a small-scale ground station using millimeter wave radar. Then I'll also cover one medical application, how to measure breathing rate and heart rate using millimeter wave radar. So start with very basics, then go to the range estimation, then concept of the RF signal, also the beep signal or the intermediate frequency signal, and then how to estimate the velocity of the targets, then how to estimate the angular arrival of the targets. So basically what we do with the radars, there are several applications using radars. I will also be briefly covering what is the scope of the radar. Also, I will be placing what are the competitive alternatives for the radar, what are the pros and cons, so that you will get a broad overview of the spectrum of sensors. So if anybody has question, do not have to wait until the last minute. I can take it in between also, no problem. So that you won't find the question after the end of the talk. So I go a bit slowly. So my objective is to transfer the knowledge, not to rush. It's very easy to work with radars. Also very fascinating sensor as compared to any other sensors. Also very reliable sensor. It is going to play a very critical role in futuristic automotive or future automotive and industrial sectors. Very, very important radar, even for medical domain, including medical domains. So I just briefly look into the sensors, what sort of sensors, especially targeting towards automotive. We have the very short range sensors, ultrasonic. Those are ultrasound signals. They are RF signals. They are ultrasound signals, sound signals. They are in the range of few kilohertz, and they work up to thousands of meters only, right? So you do not get image. It's also a range sensor, right? You basically transmit and you basically get the reflection and basically look into it. Then there are too many other ultrasound sensors surrounded by. Then you will not have that much reliability there. Then you have the short range radars. We are talking on the order of 200 centimeters to 80 meters. So operating frequency is in the range of 77 to 81 gigahertz. And also 24 to 26 band also is there. So these are the short range ones. So under 100 meters. And then you have the video, not exactly 8 meters actually, but videos are up to 30, 40, 50 meters. You do really get a good image. You can basically identify many objects in the video scope. Basically 50 meters, up to 80 meters also, but you need to have a more computational complexity. For example, when you take this data, it is basically one-dimensional data. It means you get a time series signal. It's very easy to process. You do not need much computation. Right? You can also do that on the even if the microcontroller. So this one, the radar data is also the time series data. The processing is minimal. But when you come here, video is basically images, a series of images, a lot of data to be able to store, and a lot of processing capacity are needed. Then we have the medium range radar or infrared range. So there's also 77 to 81 gigahertz band, also 26 gigahertz range. It goes up to 200 meters to 160 meters. It is still RF range. Then the long range radar, it is 76 to 78 up to 250 meters. But there are radars which goes up to 400, 450 meters also, all the way up to, you can assume, half a kilometer. So, and as compared to all these sensors, except the imaging ones, for example, RGB camera or IR camera or thermal camera, or those are imaging devices. You get full features of the targets, but they have their own pros and cons. For example, RGB cannot work when it is fully light conditions or fully dark conditions. For example, LiDAR, you need to have fine clouds. It is basically fine clouds data. It is a huge data. We have to have a lot of storage, and we need to have a lot of processing capabilities. Then at the same time, but they're very good. They give the full details. Maybe, may not be, but for example, that alone may not solve the purpose in automotive applications. The moment I talk about automotive means it's not just autonomous driving, but it could be applicable to the robots outside or indoor, or there are quite many applications apart from autonomous driving. Okay. So that is the spectrum we are looking at. Then particularly millimeter wave is defined from 30 gigahertz to 300 gigahertz range. So when you look into this one, then we have IR, then we have the visible here, and then we have the X-rays, and those are ionizing radiation, right? So we do not use for very general purpose applications there beyond that one, right? That's not very easy to work with. The moment we touch upon ionizing radiation, that is only medical applications or some special scientific applications will be going there. So these are range we are talking about 300 to 300 gigahertz range is defined as millimeter wave range. Then when you look into this one, this is microwave millimeter. So the other one is IR, I guess. So not IR. This is visible. IR visible. Yes. So this we know this is optics and this is electronic. The spatial resolution. So when you basically look at the things, the spatial resolution we talk on the order of centimeters to meters. This is millimeter centimeter. So these are the micrometers. Then the sizes when you take, so this has to be on the package. So these two are supposed to be on the package, but the micro can be on the PCB. The components on the PCB, how you make the physical device. And then the propagation aspects, basically the microwave and millimeter, they pass through. And the visible and bulk do not pass, right? So we are talking about, this is the range, not what range we are talking about. We are talking about some 77 to 81 gigahertz range. Mostly the TI millimeter radars are the dominant ones in the market, both for automotive and industrial applications recently. So few millimeters. The main advantage is that the antenna is a small dot. The whole device can be very small, like the 3 fingers can fit it, right? That's the advantage of the millimeter wave. This band 77 to 71, 76 to 77. Major countries are using for vehicular radar, also in infrastructure systems. Also 77 to 81 for the shaft range. Usually before 77 became dominant, the 24 gigahertz used to be there, but 75 to 85 is mostly for industrial purposes. What exactly radar does is basically we can measure the radial distance of the objects in front of the radar very accurately in terms of on the order of a couple of centimeters. The radial range in the sense, so when the radar is placed here, when you draw a circle sort of thing, then all the lines, all the points are on the radial range. The shortest path from the source to the target is the radial range. So that is what the radar tells. Radar tells the radial range. The shortest path from the radar to the target. Also, it is same applicable for the radial velocity. That is the direct path to the target. Then angle of arrival is basically where the target is located. For example, when you place the radar here, whether how many degrees left side, how many degrees right side, it is called azimuth angle of arrival. Then we can also tell how many degrees up and how many degrees down. That is called elevation angle of arrival. But most of the radars, most of the applications, we usually talk about only azimuth angle of arrival, that is on the horizontal plane. Okay. So these are the things we can do in the radar, right? So in addition, we can also monitor small vibrations. A huge number of applications to be able to monitor small vibrations, even including medical or any industrial processes or any motors or any changes in those small vibrations can be monitored using the millimeter wave radars, very precisely on the order of millimeters. So why radars are good? Basically, they work in dust, fog, smoke. For example, when you are when it is very foggy situation, the driving really becomes very hard. Even you cannot see 10 meters from the vehicle in front of it, right? To be able to drive safely, you need to see at least 150 to 200 meters, right? So all the cameras like this, the night vision or those things also will not work in the fog and dust. Only the radar is very reliable. Then the dark light or no ambient light, radar is reliable sensor. Also, it passes the plastic or the not very hard materials. Some materials it basically passes through. So, lot of applications. Where you want to measure the range or the velocity or the localization or the small vibrations, we have a huge number of applications. Military or weather or law enforcement or automotive industry or for example, automotive, we take adaptive cruise control or autonomous emergency braking, blind spot detection or lane change assistance or the front and rear cross traffic alert, automated parking or 360 surround protection, body or chassis in-cabin applications also. Then when you talk about the industrial applications, the fluid level sensing, very reliable one. And then the solid volume identification or traffic monitoring, infrastructure systems, robotics, many others. Also medical applications like monitoring the heartbeat or breathing rate by non-contact means. So adaptive cruise control is that when there is a vehicle in front of it, you basically adapt. You measure the range, then you adapt the speed adaptively, right? If it is nearing or it is slowing down, you basically keep on doing this one. This is very accurate. Radar measures the range, the radial range of the target very accurately, up to a couple of centimeters down. Then I talked about automated emergency brake also. Then the lane change assistance or the blind spot detection, parking and proximity warning. Here, the surround sense 360 around the vehicle and also around riding. The main advantage is that you can do with the cameras also, right? But when the moment if somebody knows working in the sensors, right? If somebody knows that that car has only the RGB cameras, it's very easy to fool. If you for example, if you put a flashlight, that's it, right? It will get confused quite quickly. LiDAR, you cannot process library, so those are point clouds. Even single frame is requires a lot of computation. You cannot do on a small microcontroller or microprocessor like Raspberry Pi sort of thing. But radar just a single time series, simple time series data. So when you look into the range aspects, the same applications are laid down here. I'm not getting into the although these will anyway the slides will be shared. So I already talked about ultrasonic, the radar comparison and the stereo. So when you look into this one, the radars all are green here. For example, most of the radars are having most of the conditions actually. It's very good for the many applications. So a few times clearly to be able to follow further. We talked about the range, we talked about the velocity, we talked about the angle of arrival. Then we have the range resolution. The range resolution in the sense, if there are two targets in front of the radar, if the radar has to see them as two distinct targets, still how close they can become. They become close and close and close. Then at some point of time, radar will not see them as two. Radar will see them as one. For example, if I say the range resolution is 5 meters, for example, then if the two targets are 4 meters apart, the radar sees them as single target. The radar tests that there is only single target. That's the meaning of the range resolution. The same applicable for the velocity resolution. The velocity resolution is how closely two targets can move. For example, if some vehicle is moving at 10 km per hour, the other vehicle is moving at 11 km per hour. If our range resolution is 2 km per hour, then radar sees that there is only single target moving. There are not two targets. Right? That's the meaning of velocity resolution. The angular curve resolution is basically when you make the cones. If I say that the angular variable resolution of my radar is 10 degrees, but if you have a cone from 30 degrees, then the radar sees, even if you have 10 targets, the radar says that there is a single target. That's the angular variable resolution. Right? Most of the time, we talk about the angular variable resolution on the horizontal plane. It's called azimuth plane. The horizontal only. Radar will not tell vertically. You can tell vertically also, but we need a lot of antennas in the vertical direction as well. Right? Most of the applications, we usually look in the horizontal plane. So horizontal plane in the sense, very first slide I have shown. Also later also I will show some slides here. So you basically have this sort of figure. Right? So when I say, so this is the horizontal plane. So when you look into the vertical side, so that's the vertical plane. That's called elevation. This is called azimuth. Horizontal is the azimuth one. The vertical one is the elevation one. So this is the horizontal field of view. How much wide the radar can see. How much wide the radar can see is called horizontal field of view and vertical field of view. Then this is angular parallel resolution. For example, if I say that this is a 10 degrees, then if there are two targets within these things, if the radar range resolution is 5 degrees, if there are two targets within this segment, then the radar sees them as single target. That's the range resolution. Okay. Yes. We are clear on the basics now. I will start with the very basics. I will quickly finish the basics and I will get back to the main applications. So what the signal we use in the radars, so especially millimeter radars, is basically the FMCW radar. It is frequency modulated continuous wave radar. So the signal is basically here it is the time domain waveform is shown here. On the y-axis it is the amplitude and on the x-axis it is the time. You basically linearly increase the frequency over the time. When you look into what is in the frequency spectrum, basically on the time is same. So you are basically increasing the frequency here. So we are starting at 77 gigahertz and going to 81 gigahertz in a span of 40 microseconds. We are speaking 4 gigahertz. This 4 gigahertz is called RF bandwidth. The advantage of millimeter radars is that we send the RF signals, but we process the IF signals. We do not process the RF signals. We basically process the IF signal. Okay. So this is called the bandwidth. So here RF bandwidth is 4 gigahertz. This plays a critical role in resolving capability of the radar. For example, if somebody is interested in resolving very closely spaced targets, then obviously they should look for the radar with more and more RF bandwidth. So the slope is defined as here. The bandwidth step over the time, it is 4 gigahertz to 40 microseconds. So the longest target, if you transmit the signal come back from the longest range of the radar capability within the target, that comes in the fraction of this signal. For example, if I have a 40 microsecond signal, then the reflection usually comes for the maximum range target, a fraction of even 5% of this one, maybe within 5 microseconds. If the reflected signal comes after 40 microseconds, you will not be able to find that target. Right? Right? Why? I'll come back to that. Why? So how the basic radar works is basically we basically have the synthesizer. Then we make the FMCW signal. We use the transmitter and we transmit the signal. The FMCW signal is nothing but a linearly varying frequency signal, a repeated of that signal. It is basically sawtooth wave. When you look in the frequency domain, not on the time domain sawtooth, it is on the frequency domain sawtooth. Okay. Then that signal is transmitted. Whatever we think that there are objects like things, right? If there are any obstructions or objects or targets, the signal will get reflected back. That reflected signal and transmitted signal will be mixed. Then you generate various signal. Here we are basically transmitting on the order of gigahertz range. When you mix, the signal you get is basically on the order of couple of megahertz. Here you are using 4 gigahertz range, 77 to 81 gigahertz range bandwidth. Here we usually get for the same 4 gigahertz band, we get IF signal on the order of a couple of tens of megahertz, 15 to 20 to 30 megahertz. We are going to process that 30 megahertz signal. That 30 megahertz signal is a time domain signal, time series signal. Okay, this mixer is basically takes the transmitter signal and the receiver signal. It basically gives the difference of the two signals. That's why we get the low frequency signal. That's called a beat signal or also IF signal. Okay, so that is the IF signal. Okay, when you look into what this IF signal is, basically to have a more closer look. So we use the frequency map. So that's very easier to understand. So this is the frequency versus time. So this is a transmitted signal, and then we get the reflection. The reflection is coming back within a small fraction of the total time of the chirp. The FMCW signal or the radar signal is also called chirp, CHIRP. Okay. So then the transmitted chirp and the reflected chirp, they both go to the mixer. Then we get a different signal. So the different signal is basically this one. So when you do this, basically the linear equation y is equal to mx. Here x is tau, then the slope is s. So this difference is basically s tau, right? So the difference is basically the frequency. Right? It is on the y-axis. So the difference is frequency. So that signal is basically s tau. That is single tone. If you have a very perfect target, and if you transmit signal, if you transmit one chip or one FMCW signal, then you get a reflection, you get a perfect sinusoid here, single tone frequency here. Right? What is this tau? Is basically when you transmit the signal should go to the target and come back. That is basically 2 times the distance to the target from the radar over the speed of light, because we are using the RF signal. That is 2D over C. So this tau is basically 2 times range over C from the radar to the target distance in the range. So the frequency is basically S2D over C. These are fundamental. These are most fundamental to be able to understand the radar. Right? This is how we find the radar. Basically, you get the signal, you take the FFT, you find the frequency, you put the frequency here, and then you know the slope, you know the tau. The tau is 2D over C. Then you basically equate this one to the frequency, then you know the slope and you know the C, you basically find out the distance. If you know the frequency peak, means we know the range of the target from the radar. Okay. So the next question is, we take that FFC signal, we basically take the IF signal. All the radar processing will be done on that basic IF signal. That is carrying all the information of the targets. So basically about FFT, if you have a time domain signal, then you get a peak nicely, right? So here I have two signals here, because I'm going to explain later how the radar resolves two closely spaced targets. What is the fundamental mechanism? What is limiting it to be able to resolve how much closely targets the radar can resolve, can still see them as two distinct targets. So for that, you need to understand a little bit on the basics of the FFT. So here there are two signals here. So there is a blue signal and there is a red signal. It is basically simple time domain signal. If you see, the red signal completes 2 cycles. The blue one completes 2.5 cycles. It is going 1/2 cycle extra, right? Just 1/2 cycle extra. If you give these two signals to FFT, combine one, the FFT says it has there's only one signal. It is only one frequency, because the FFT is not able to resolve because it is only half cycle extra. When the moment you double this one, you basically quickly see the two peaks, right? The two peaks now. So what is this difference can be resolved is directly proportional to the 1/T. If you have the longer observation period, the 1/T will become smaller and smaller. The smaller and smaller frequencies can be resolved. Why we want to resolve smaller and smaller frequency differences in the IF signal? Because if there are two closely spaced targets, they produce two peaks. If those peaks are very closely spaced, we want to resolve. If you will have to resolve that one, we need to observe for longer period. If you will have to observe for longer period, obviously you have to increase this one. If you want to observe for longer period, you have to increase the TC. When you increase the TC, you basically need to increase your RF bandwidth. That is the reason. Okay, let's come back here. Okay, if there are multiple targets, in front of the radar, then you basically get the multiple reflections. Then you get multiple peaks in the IF signal. If you take the FFT, you get all peaks. So you pick out this frequency F1, F2, F3. You basically go to S2D over C and translate the frequencies to the range. The peaks are directly related to where the target is. The lower the frequencies, the target is very near. The higher the frequencies, the target is much further. The higher the amplitude, the bigger the target, or stronger the reflection, right? For example, if you have a drone, or if you have a human, or if you have a car at same range, you get a lower peak for the drone, you get a bit higher peak for the human, much bigger peak for the car. Also, when you use a radar on the drones, that will become much more reliable as compared to on ground. For example, when you use on ground, you get multiple reflections from ground as well as other obstructions. We have to deny that. Okay? Also, you will get very easily interference that you will get in the drones as well. But in drones, especially when the radar is clear, that is the free space, right? You will not have any ground clutter, all those issues. It is much more reliable for drones as compared to the on-ground vehicles. Okay. So that is about the range resolution, right? How this is directly related, we will look into. So as we know, the difference of the frequency is the more and more observation period we will have, the smaller and smaller differences we can observe. The maximum you can observe is basically 1/T. That the difference of the two frequencies contain how closely two frequencies can be in a signal, still be seen as two distinct peaks, is directly related to this one. So this delta, that is S2 delta D over C. And then if you rearrange all those things, then this delta D greater than C over 2STC, that is C over 2B. 2B is the bandwidth. RF bandwidth. If you put more and more RF bandwidth, you can resolve more and more closely spaced targets physically. So that is translating to if you have a 4 GHz bandwidth, so we can resolve up to 3.7 cm. It means that two targets still they can become as close as 3.7 centimeters, radar still sees them as two distinct targets. When the moment they are below the 3.7 centimeters, the radar sees them as a single target. That's the meaning of range resolution. Okay, and then here we're talking about what is the maximum range the radar can see. But this is a fundamental limitation. One fundamental limitation is coming from the sampling rate, because we get the basically get the IF signal. That is one limiting factor is the IF signal sampling frequency. The another limitation basically is the fundamental limitation is coming from how much power you basically transmit. I'm not going into the details of those fundamental limitations, but usually the radars available in the market, they can go all the way up to the 450 meters. You can reliably see the targets. Where the challenge comes is if you want to observe very tiny drones, for example, very small drones, bird-like drones, or very small drones, then that is challenging. Right? Since those will be the phase space, it is still possible to detect. If we will have to do the same things with the RGB or IR or LiDAR or thermal, it's impossible. Because when the moment you cross 10 meters, you hardly see anything. Although machine learning works only very well when the object you are interested in, if you want to classify it, that has to occupy a large portion of the image, at least 5% to 10%, right? If you have a very small drone, if it is occupying only less than 1% of the total image, then you hardly see it. Any machine learning hardly see it, right? That's the challenge. For the most of the imaging based devices will fail when you will have to look at very small targets. Also, very closely spaced targets is also important, right? For example, when you are using autonomous navigation for drones, the drone has to know how many other drones are there. For example, if they are very closely spaced, if the drone is seeing only single target, then if it makes the path planning, and then suddenly some other drone appear, then it will not that path planning will not work. For example, right? So that's the important thing. So this is summary. So we basically get even if we use the RF signals, RF range, we get IF signals. The IF signal frequency peaks we are talking about, those peaks are directly related to the range. The range resolution is directly related to the RF bandwidth, and then the maximum range is defined by the sampling rate of the IF signal. So when you compare with the point clouds, the latter is also very good device, but only the issue is that it's not a time series, single time series signal. Like we get a single time series signal, we just take FFT, that's it. FFT is not a very fast effective. You can do in a couple of milli to micro down, right? But on the other hand, when you look at the point cloud or when you will have to process the image, it is a huge information has to be processed. So this information can be done on the order of milliseconds, where we have very strict requirements on the latency to be able to calculate, to be able to take the decisions, especially the autonomous navigation, both for onboard as well as for the drones. And in addition, this will work up to a couple of hundred meters, up to 450 meters, right? Then it is very easy to take the decisions. It is very easy to make the path planning. We get enough time, right? 450 meters, even if you calculate a couple of tens of kilometers per hour, we will get enough time to be able to basically make the reliable path planning as well as avoid the collision occurrence, right? So that's the important. On the other hand, if you will have to rely on RGB or thermal or other one, it is computationally expensive. Moreover, The drone is on the air, right? The power is the most precious thing on the drone, right? As long as our computational power is not even a fraction of the drone's power, that is okay. But when the moment the computational power is becoming comparable to the drone's power, there is no more room, right? If the drone goes for about 2 hours, then if a computational power is also taking the equal amount of power, then drone goes only for 1 hour. That's very rare. Okay, so all the algorithms that will be put on the drone has to be computationally very efficient, power efficient. So any signal, when you're talking about, there will be 3 properties, right? You basically have the frequency, you have the amplitude, and you have the phase, right? So amplitude, also you can manipulate some things with amplitude. For example, when you have IF signal, so when you basically tell like whether the target is big or whether the target is small or not, but you need to have a lot of data to be able to make that classification. On the other hand, frequency is basically telling the range. Doesn't matter about the amplitude, but frequency is directly related to the range because it is basically a time of flight, right? So that is what is deciding the frequency. So the component. The only other component left is basically the phase. How to exploit the phase to be able to tell other things about the targets, for example, velocity or the angle of error. So the concept of phase is like the starting of the signal. You have a time series signal here, so this is amplitude versus time. So when you take FFT, so here the phase is 0 here, so you have the single peak here. So we will also show the phase. Basically, when you take the FFT, you will get the amplitude versus frequency. You will also get the phase versus frequency, right? At which frequency, how much amplitude is there? At which frequency, how much phase is there? Right? That's what FFT gives. For example, if you have the signal, so here the phase is 0 here, the phase is 90 here. You get the single peak here, so it is the peak frequency is same, but the phases are different. So here you get 0 phase, here you get the 90 phase because here, the phase is 90 here, right? We know that the frequency tells the range, right? That is the longer changes or the longer ranges, basically. Then the other important thing is that when you have the signal here, so you are basically starting the frequency linearly, the slow frequency going from 77 to 81 gigahertz. For example, if I shift my entire signal by one time period, how much will be the phase change of the signal is basically 360, right? If I shift my entire signal by half period, then the phase change of the signal is basically 180 degrees. If I shift my signal by 1 quarter time period, the phase change is basically 90 degrees, right? So if I put it into the equation, then it is basically 2 pi. F is basically 1 over t, that is the starting of the frequency of the signal. 1 over t. If I make delta t move, if I make this delta t by one entire time period, then my maximum phase difference for one time period is 2 pi. If my this delta tau is less than, if it is between 0 and 1 time period, then my phase change is basically between 0 to 360 degrees. That's what is the meaning of when you basically move the signal or the shift the signal, right? So this is the generic equation, right? When the signal goes and come back, you basically have the 2 delta t. So this f equal to n lambda is all this rearranged and the equation is put here. That is in terms of the distance from the target. So this is the frequency of the IF signal. This is the phase associated with the IF signal, right? Let us look at one 1 millimeter change of the target. Whether we can see that one in the frequency or whether we can see that one in the phase, right? So we know that the frequency, when we calculate the frequency and all, So that is leading to 333 Hz. So 333 Hz, we are looking to this 40 microsecond time period, that is 0.013 cycles. If I move the target from the present position by 1 millimeter back or front, that is causing the frequency change in the IF signal by 333 Hz, though it is only 0.013 cycles. If I take FFT, will I be able to see that change of frequency for 0.013 cycles? Even if I double, then I will get 1 over T, right? So this is so small when you compare with the observation window. This number of cycles that is causing this frequency change is so little. We cannot observe the frequency change. The frequency, if you take FFT, even if the target has been moved by 1 millimeter, if you take FFT, you will still see the same frequency, but not this small frequency will not be visible because it is so little to be able to observe, because it is very little in the observation window. On the other hand, if I calculate the phase difference, that is coming as 180 degrees. My phase can go from 0 to 360. The 180 is too much for 1 millimeter. If I change anything my target in between 0 to 1 millimeter, then I go all the way 0 to 180. Right? It means that very small changes in the target ranges, phase is the more valuable thing than the frequency of the IF signal. Right? That's why we pick the phase. So if I have a single target, for example, then I send one FMCW signal, then I get the reflection from the target. Then we have one IF signal, other one beat signal. Then we have the phase and we have the frequency and phase oscillating this. Then if you send the one more signal after some time, then you get the same IF signal. If it is only small difference, you get the peak at the same, the frequency peak at the same location, but you get the different phase, right? That phase, for example, if I send one IF signal, then I get one phase here. After TC, if I get one more radar signal or one more FMCW signal, then I get one more IF signal. Then I will have the phase here. This phase difference is measured actually, right? That is equal to, this is 4 by delta D, right? So during this TC time, the distance it travel is basically VTC, right? When I send the first FMCW signal, then after TC, if I send second FMCW signal, the target moves within the TC is basically VTC. The target is moving with velocity V. Right? So really, if I can measure this phase difference between two chips, then I can calculate the velocity of the target. A single target I am talking about. Right? This is how you basically measure the velocity of the target. This is the second fundamental principle regarding the radar. Okay. For example, if there is a vibrating body or a heartbeat or the breathing rate or the chest movements can be captured with the millimeter wave radar, because the millimeter wave radar is very sensitive. Even 1 millimeter changes, it is changing 180 degrees phase, right? If it is sub 1 millimeter, then we have a broad spectrum of 0 to 180 degrees, right? So if there is a vibrating body is there, for example, so that is vibrating at delta T. So it is going up and going down, going up and down. And then if you send the first chip, second chip, third chip, and up, you get the same frequency, but the phases will be different, right? Phases will be different. So you basically plot these phases. It's going like this, and from the phase, you can calculate the distance. So from the phase, you can calculate the distance. Also, with how much frequency the body is vibrating, if you take one FFT on this, then you get the frequency as well. With how much frequency the body is vibrating, with how much frequency, with how much amplitude it is vibrating. Okay, so this is what exactly will be exploited for the medical applications. For example, if you will have to monitor the heartbeat, or if you will have to monitor the breathing rate, very accurate, pretty accurate. Also, if you want to monitor any vibrations by non-contact means, even the breathing rate by non-contact means, or the heart rate by non-contact means, you can just put the millimeter wave radar. Millimeter wave radar is non-ionizing radiation. It is much lower than the visible range, so it is pretty safe. It is not ionizing radiation. It will not take out any electrons or the neutrons from the cells, right? It is pretty safe. So we can easily measure the breathing rate and heart rate. So especially when you want to monitor the small vibrations or the frequency changes of the vibrations, to be able to, for example, most of the applications, before they break, they vibrate at different frequencies, right? You can basically monitor the frequencies as well. Also motors, before they wear and tear, their frequency changes. So those small vibrations can be monitored with the millimeter wave radar by non-contact means. Okay, basically to be able to tell the range, we need one transmitter and one receiver. You just send one every signal, and you basically receive. Even if you have multiple targets, you will be able to tell the range of all the targets. If you will have to tell the velocity of the single target, you need one transmitter and one receiver. You basically fire one chip and the second chip after TC, then you basically calculate the velocity. If there is only a single target, if there are multiple targets, basically you fire a series of chips, right? The gray ones you see, right? So this is basically, these are the chips. Whenever we transmit a chip, there will be IF signal associated with it, right? If I send 256 chips, then there will be 256 IF signals, right? If there are two targets actually approaching the radar, if there are two targets approaching the radar with a velocity v1 and v2, these 256 IF signals are carrying the information of the targets, both the range as well as the velocity, right? The range is carried out over the frequency of these components. If they are almost equal distance from the radar, then the peak is at the same location, right? If they are moving at different velocities, the phase associated with these two targets are embedded in those 256 signals. If I will have to extract the two phases embedded in it, I will have to take one more FFT on this first FFT. When I take FFT, this is a complex baseband architecture. The IF signal I'm talking about is basically a complex signal. When I take FFT on the complex signal, we'll get one more complex signal. So on the complex signal, if you take second FFT, if you repeat the phases of those things, those two phases can be figured out, and those two velocities can be calculated. If it is only a single target, I will not need 256, or I will not need 128 or 256 chips to be fired to be able to tell the velocity of the target. Single target. If I want to find the velocity of a single target, I need just two chips, one transmitter, one receiver. That's it. But if I want to tell the velocity of the more targets, I need to fire more number of chips, right? How many number of chips you fire? For example, if you go to 2 than 512, than 1024, then you basically resolve more and more. That's what is FFT, right? You make more bits, right? If you have more samples. Okay. That is the velocity estimation. Okay. Then the final concept before going into the going to show one automotive application, especially setting up the ground station. Then other application in the medical domain already I have explained, but I will show how we have made practical. And then the other concept is the angle of variable estimation. This we are talking about only on the horizontal field of view, right? We are not talking about the vertical field of view, horizontal field of view. So what radar tell basically is that how many degrees from the left to the radar and how many degrees right to the radar. That's what the angle of variable. Radar can tell maximum 90 degrees left and maximum 90 degrees right. Nothing more than that, right? Because radar cannot see that. Right. So maximum ideally theoretically possible field of view is 180 degrees minus 90 to plus 90 basically 180. How we do is the angle of variable. What is the drawback of the radar is the accurately estimate the failing of accurate estimation of the angle of variable. We need more resources to be able to do that one. For range and velocity, we do not need more hardware resources. We need just more computational resources, especially for the velocity estimation of the multiple targets. For range and all, you do not even need more computational resources. But velocity estimation, we need to find more and more number of chips, but only single transmitter, single receiver. On the other hand, to be able to estimate the angular variable, we need more physical antennas, physical transceiver elements. I'll come back to that one while. For example, when you have the radar here, when there is a target here, the target moves by delta D. The phase change we talked about is basically 4 pi delta D over lambda, right? The same concept, if I rearrange this one, if I have the target here, I have the first transmitter here, then I have basically two receivers here. Basically, the signal goes to the target, and the reflected signal will come back to the two receivers. These two receivers are physically spaced on the PCB. Okay. The target sees the different distances, right? So the reflected signal to the first antenna travels d distance. On the other hand, for the second antenna, it travels d plus delta d distance because it is physically not in the same location. It is a bit away from the first antenna. So that's why this additional delta d is there. Okay? For this additional delta d, we have the phase difference between these two IF signals because we have one transmitter and the reflection is coming to this receiver. Then this transmitter and this receiver, we will get one IF signal, and the second receiver and the first transmitter, we get another IF signal. This is the phase difference we are talking about. That phase difference is 2 pi delta D over lambda. Here 4 pi delta D over lambda because this delta D here it is going 1 delta D here and 1 delta D coming back here. That's why it is 4 pi delta D over lambda. That is the phase difference between the two receivers, physically spaced receivers. This is the same phase difference we talked about when we were estimating the velocity. But what is that one? That is a temporal, right? We fired one chip, then after TC, we fired another chip, but it is the same receiver. One IF signal we got, then after TC, then the second IF signal we got. We are looking at the phase difference between those two IF signals, but it is the same receiver. But here, for the angular variable estimation, we are talking about two physical receivers sitting on the PCB. We need at least two receiver antennas to be able to estimate the angular variable of a single target located in front of the radar. Two physical receivers to be able to tell the angular variable of a single target. So if I place this radar, then if I make this angle theta, then if I make the 90 degrees here, then this is 90 minus theta, then this total is 90. If this is 90 minus theta, then this is supposed to be theta. Then this additional distance is supposed to be d sin theta. Right? If I put the same equation back here, this is the delta d sin theta. This is delta by phase difference. We measure between this IF signal and this IF signal. This is the phase difference we physically measure. Then we equate that one 2 pi d sin theta over lambda. Then you basically get the theta. That's the angular variable. If it is single target, it's fine. If there are multiple targets, what should I do to be able to tell the angular variable of multiple targets? If you understand so far. For the velocity estimation of the single target, if I have one transmitter and one receiver, if I want to estimate the velocity of the target, if I fire 2 chips is fine, right? If there are multiple targets, what I was doing, I was firing multiple chips to be able to tell the velocity of multiple targets. If I will have to tell the angular parameter of the multiple targets, what should I do? Huh? What I would do is, I would put more receivers. The more and more receivers I put, then the more and more targets I can resolve, right? So if I will have to have the more resolving capability for my radar regarding the angular variable, I need to have more number of physical receivers sitting on the PCB. That is expensive. That is hardware expensive, right? Maximum number of, it could be transceiver based. It doesn't have to be one transmitter and 10 receivers, but it could be complex. For example, 3 transmitters and 4 receivers can make 12 transfer pairs. That will also account for. This is a fundamental limitation for the radars available today. You cannot estimate the angular variable more accurately. Even if you have the 12 transceivers, the angular variable resolution is basically coming to a fundamental limitation after doing all the math. That is 2 over n. It is number of physical receivers. For example, if I have one transmitter, if there are 10 receivers, it is basically 2 over 10. It is basically 0.2. If you do all the math, the range resolution, the angular variable resolution will come around 10 degrees. 10 degrees. If I have a 10 degrees cone forming, very near to the radar is fine. But when you go to 10 degrees far and far, you can fit many targets in this core. Radar sees them all as single target. That's the drawback for the radar. That is the only drawback for the radar. So that's why when somebody starts working with the radar, if they want to work with angular variable estimation, they will get 0 resources, even from Texas business, because that's not working. That doesn't work. That's why they do not sell those aspects. They sell basically accurate range estimation, accurate velocity estimation. These two are very perfect for the radar. But if somehow you can use the range estimation and velocity estimation to be able to find the angular variable estimation, that will become more accurate. Because the range estimation is very accurate, the velocity estimation is very accurate. They do not depend on the hardware constraints. They do not have any hardware constraints. They have only computational constraints. The velocity estimation has only the computational constraints. Okay, that is about. I'm not putting all these maps again. So just making a comparison. Even these slides are available. So what we have done is the range can be estimated very accurately. The velocity can be estimated very accurately with the radar. Only drawback for the radar is how to estimate angular variable. So that we will make some improvements in this line. What we have done is that we have basically, we do not want to make use of the traditional estimation of the angular variable because that also has the limitation of the phase changes are very high. The target is right in front of the radar as compared to the targets that are left side or the right side. After the angular variable estimation by the classical method is not at all accurate. So then what we have done is that we have mounted the radar on the rotor. Basically, we put the radar on the rotating rotor, and then we swept the transmitting signals, right? Then we basically calculate only the range profile. For example, if I put my radar on the rotor, if I sweep from left side to right side, I'm sweeping 180 degrees, right? If I fire for each degree one one IF signal. Then I basically one IF considerable signal. Then I basically get 180 IF signals, right? I am putting this 180 IF signals for one IF signals for each degree, right? Then I'm basically stitching together all these 180 IF signals for 180 degrees, right? It means for 180 degrees, I'm having range profile plotted in the vertical direction. If I make the heat map, then I will know where the targets are located. The center point of the location will be my target location. Okay. The radar is placed like this. So that radar will be rotating like this on this. Then we, for example, when we rotate the 180 degrees and 180 chips, then we have 180 IF signals. Those 180 IF signals are basically stitched together, right? You may have peak here, you may have peak here, you may have peak here, right? Those are all stitched together. If there's a target located here, then when radar is sweeping, when it sees the maximum body, the reflection from the target, then you will get the peak around the center of that. When you're sweeping like this, you get this range angle maps. Right? This requires only the range FFT. Right? When I have this map, then I can use the YOLO like algorithm. Then I can make the bounding box around this one. These are basically called the radar signatures. And then the center point of this one will be my angle, because I'm plotting the angle versus the range profile. This is basically showing the heat map. Actually, this is basically the range profile. If I make the drawbacks around box around this one, the bounding box around this one, if I make the center point this one, the center point is basically related to the target. That's how we have estimated. So these are not for free because we have to rotate the radar all the time to be able to find. But we can rotate 360, right? That's the beauty of this one. Okay. So we have done the several measurements in the open field, and we have made the when you basically stitch the FMTs like this, so you have the range profiles all is going like this. So when you are stitching like this, it is basically going from 0 to 180 degrees. This range profile is we basically stitch it on this. Then we have made them as the heat map. So that's why we are getting the radar map like this. For example, this one is the case D. The person is local. For example, you have label here A1, A2, A3, A4, A5. It means it's basically with respect to the radar, the target A1 is located at 0. It is completely left side and at 5 meters from the radar. The target is A2 is basically 30 degrees, then 7 meters up distance from the radar. Then target A3 is basically 60 degrees with respect to radar and 9 meters, and it is basically 90 degrees, then 11 meters. And we have made several instances of this one, and we made the measurements. Then we have run these images using the machine learning to be able to get the bounding box. When you have the brightest spot, so that will be the center part of the target. Then we will look into the angle there. Then we basically tell that this is the angle of arrival of basically that particular target. We're not done the thorough exploration of that one. What is the resolution capability of this method? And although we have not explored, but the method works very well. We can accurately estimate the angle of arrival, but we do not know what is the resolution capability of this one. So these are this machine learning one. Also, we have classified actually, because when you look into this one, this is basically, if you look into the radar signature, it is basically going and sweeping, right? When it is a human or drone, the signature, the reflection will be a very small quantity. We will not get a bigger signature there. But on the other hand, if it is a car, you get a bigger signature. So based on the signature, also you can classify whether it is a human or drone or dog or cyclist or those things you can classify. Though it is not a perfect RGB sort of thing, but you can if we have the measurement data with all the targets, if we get these nice images, then we should be able to classify it. Not 100% accuracy, but certainly 97 to 98 above. So for the UAVs, we have out of 650 instances, we have out of 664 instances, we have classified 650 as right and 14. The model got confused. Maybe that treated as humans. And car out of 670, we have 660. The car is bigger upside, and we always get the bigger signature, even if it is very long distance from the radar. There's only one fail. Maybe it is the very longest range. The humans, out of 969 instances, so we have 14 fails. So that is pretty accurate. Even if you all the machine learning algorithms and classification using the RGB data or any other imaging data is a perfect setting. You have a nice pictures, nice all those things. That will work very well actually. But really, when you start taking the data a bit away, for example, more than 10 meters or more than 20 meters or more than 30 meters, your classification accuracy will go much worse. So if you will have to use for own your application, you will definitely not use RGB. If you will have to use for your own purpose, I don't think you will use RGB, and you will depend on that. You certainly go for that. Okay, this is also we have made the how close, how much is the deviation of the angle where the target is located, and how much is the deviation using our method for various objects. So it is on order of 1 degree deviation, the estimation. So it is the comparison of that one. We have additional material. I'm skipping that one. I'm going to very important application. Breathing rate and heart rate monitoring. So usually we have an automated procedure, right? When you have a perfect setting, your radar, if you basically start in front of the radar, you can get the heart rate and breathing rate pretty accurately. It's fine, but people have different heights and different shapes also. So we made automated, right? Radar can do the measurements very accurately, that's no problem. But pointing the radar perfectly towards the heart is the problem, right? If you will have to do manually, you have to tell the person who is to whom we have to measure. We have to steer manually, or we have to tell the person to face the radar properly. But if you have automated procedure for this, to be able to steer the radar towards just perfectly towards the heart, then that will be the best. Right? So most of the heart rate of the breathing rate mechanisms are contact based sort of thing. The ECG, pulse oximeter, TPG, or those non-contact based. You can also use a camera based one, but you need to have a lot of processing. The radar one is very popular, becoming very popular now. It is also more accurate. Then what we propose is the automated one. So we basically this is the PTZ camera. PTZ means pan, tilt, and zoom. And this is basically radar. We basically mounted the radar on the PTZ camera. You can pan or tilt and zoom also. You can zoom digitally, and you can also pan tilt. Tilt means you can tilt like this, also you can pan. So what the overall procedure is basically, we put this camera. This camera basically finds the person's face. Basically, face is identified. Once the face is identified, so basically in that orientation, that goes few steps down, tilting and panning few steps left. Then that will be locating the heart. The camera is used for locating the heart. once the heart is located, then we start taking the limit of our measurements. Then we use the phase calculations and to be able to do the heart rate and the breathing rate. That's the overall concept. This has been published in the articles as well, very recent. So this is the most this is medical, the non-contact based one. This is the latest work available in entire the non-contact based measurement for heart rate and breathing rate. Even if you search in the Google entirely only, this is the only work. So then we also made automated classification of low breathing rate, or the low heart rate, or the breathing normal, heart slightly low, and breathing high and heart normal. We do not have much flexibility on the heart, but by taking measurements, right, we cannot control the heart, right? It's very easy to control the breathing rate. We can tell a person who is giving the measurement, we can tell breathe slowly, breathe normally, breathe high, but we cannot tell that you get your heart high and low and right. So whatever we got, so that's why we do not have the classification for heart exactly like the breathing low and breathing normal and breathing high. But heart and heart, we basically got heart slightly low and heart normal and basically heart low. And we have to live with what we get from the persons. So one of the popular techniques to be able to, when you have the time series signal, when you have the images or videos, it is a perfect setting using the CNNs, because CNNs work very well on the images. For example, the classification tasks, the tasks, CNNs are still best. CNNs are the best. If you are working with any non-imaging data, it is better to convert your data to the imaging data. Whether it is time series signal, or whether it is heart measurement, or it is EEG or ECG, somehow you get the image sort of thing, not the time series data. If you have time series data, you have with LSTM, all those methods are also will not be pretty accurate. So it is better to come to the image domain, and then you have a nice freedom to use the CNNs for basic classification. So we have used the continuous Fourier transform. So the continuous Fourier transform, when you compare with the FFT, when you have a time domain signal, if you take the FFT tells what are the frequency component. It doesn't tell at what point of time the frequency is happening. On the other hand, Fourier transform, if you take the Fourier transform, it will tell what is the frequency component, also at what time is happening in the signal. So doesn't make difference between the Fourier transforms and normal FFT, right? So the Fourier transform basically tells in relation to the frequency components at what time instant actually they are happening. That will tell the time information as well, along with the frequency information in the time domain signals, other time series signals. So we basically can convert any time series data to the time frequency parts. Also, the Fourier transform also can be used to decompose the signal. For example, if you have a single signal, then you can also decompose that signal into sub signals. Those sub signals exactly not like FFT. FFT tells already basically, right, what sort of frequency components are there. It doesn't tell anybody at what time the frequency components are happening. But when you use the applicable Fourier transform, for example, you can take the time series signal, you decompose, you will get a subband signals, and those signals where exactly those frequency components are happening on the time axis as well, it will tell. Right? It is pretty accurate way of splitting the signal in the time domain and where the frequencies are actually happening. When you basically take the FFT, it will not tell all those things. When you take the FFT, you will lose the time information already. Because in the moment you go to FFT, that will only talk about the frequency component. That will not talk about at what instance the frequency is happening. That's all the important things most of the time. So what we have done basically, we have got the breathing signal or the heart rate signal. Then we converted that one to the image domain using the continuous Fourier transform. Those images are trained with the CNN. Then we have got a classification. That will become more accurate as compared to directly taking this one, and even if you use some other methods, that will not be pretty accurate. Most of the time, the continuous Fourier transform or the empirical Fourier transform or the short-term Fourier transform or the synchro space Fourier transform or synchro extraordinary Fourier transform. There are a couple of things. For example, if you have the ultrasound signal or the acoustic signal, then the male spectrograms will work better, right? So depending on that, depending on the data, depending on the frequencies, how closely they are spaced, you can experiment with one or two transforms. You will basically achieve higher classification accuracy than the moment you go to CNS. So this is the overall setup I'm talking about system, how that works. It is basically the overall things is explaining. I will move on these slides. So this is the one we have made the mount for the camera. We actually hook this mount on the camera, then we mounted the radar on this so that when camera pan tilt, the entire hat of this where we are mounting the camera also moves there. So these are the breathing waveform, but this is a part waveform. This is just displacement, so there any profile. You can actually clearly see the measurements accurate or not. You basically breathe how many breaths per minute you are actually controlling. You can actually check this pretty accurate. So this is the final setup look like. This is actual camera. Then we put a mount and we mount the radar there. Then we give the several measurements of several people in front of the radar. Basically, it doesn't have to guide anything. They just come and sit or stand, then the camera moves automatically and finds the face. Then it will basically tilt and zoom and locate the heart and start taking the measurements. So these are the heart waveforms. Then when you take the continuous wave transform, you get the images like this. It's very easy to classify these things than these things with the CNNs. Right? I'm talking about this. When you take the continuous wave transform, you get the image sort of thing. So the first one is basically low, the second one is high, the third one is the normal. Right? Our visible eye itself is able to tell the distinction, but on the other hand, when you see that, you will not be able to tell quite quickly. Though they are also distinct. When the moment you inspect with the visual eye that they are distinct, the CNN mostly touch on the first trial itself more than 99% accuracy. It's in the classification. Even if you cross 10 classes, that works pretty well. But if you have 10 classes like this for some other application, directly feeding the time domain signal will not work. Usually go like this, it will work perfectly. Most of the medical domain, maximum number of times, if there are time domain signal, EEG or ECG or any time series data, people are converting to one of the wavelet transform, then they are applying machine learning. So we get the pretty much accuracy around 86 or 87%. So these are the very lightweight one. We basically do the machine learning, not the huge ones, huge machines, basically on the Raspberry side. very lightweight models, very lightweight and very small inference time. So that's pretty much about the medical application. Then this is the group homepage, and time to time I have a lot of internships I have in a wide range of areas, all sensors and signal processing and machine learning, all sensors, automotive and industrial, also the wireless communications and medical imaging, so those aspects as well, and medical devices as well. So if somebody is highly interested, they can basically contact me. So that's it. Any questions? Yes.
Regarding that, if there are different angles, as you were saying, the number of receivers should increase, right, for
Yes.
estimating more number of angles. And you said that they can be like, just different antenna elements, right? So if we construct microstrip patch antenna or something like mine, like what should be the difference between this, the distance difference between the receivers?
That is on the there is a MIMO formula for that. It is on the order of lambda one lambda or lambda by 2.
In case of millimeter wave.
Yeah. So that's a small distance. It is on the order of 1 millimeter or 2 millimeters.
We can directly take a single MIMO antennas and we can use
That's what even if you use the MIMO, you have 3 transmitters and 4 receivers. If you do the MIMO, you get 12 transceivers. Only 12. If the 12, you can achieve maximum 10 degrees, not 1 degree. 10 degrees is
simple beamforming something like that.
beamforming. How much you can do? But it is limited, right? That's why we rotate. We try beamforming that is what then we rotate it. Basically, that work well because that is depending on the range profile. Range profile is pretty accurate. Whatever you do with the millimeter, the main tip is whatever you do with the millimeter radar, make use of any further processing based on the range or the velocity. That will be pretty accurate without any question. The moment you touch upon on the angle of arrival, if you try to do angle of arrival directly with the classical or traditional method, it will not work. That is the drawback of the radar. That's the drawback of the radar. We have to live with that.
Second one is like as you said, like you have to increase the bandwidth to get better resolution.
Yes, the range resolution. Yes.
So, but if we keep on increasing basically if we are concerned millimeter wave range, then can we say that we are restricted in range, like if we are trying to increase the bandwidth?
Yeah, of course.
So we can say these are just for short range and only for only short distance thing.
No, I think.
Long distance we won't be able to get better resolution.
Of course, if you increase the frequency, you will not go longer. That is for sure. That's for sure. But TI is surprisingly going up to 450 meters in free space.
Yes, I'm asking like that. That's
450 meters with this millimeter radar operated with power bank, not any other power bank. Pretty decent because no other sensor will do 450 meters. After LiDAR does, but LiDAR you cannot operate with power bank. You need a huge power and huge. Raspberry Pi will not be able to process the LiDAR data because it is a huge point unless you do compression and all those things, and you go to another dimension. But LiDAR is very expensive and also it is power expensive. But 450 meters is a pretty decent one to be able to make any path planning or any decision you want to take or any thing. That is a pretty safe, much more safe margin than required. Even if you are 150 meters, you can take decisions actually very reliably and you can make the path planning. But 450 meters is like too much distance actually. You can do many things. So you have a lot of time to be able to.
I'm assuming a scenario when there is a ground and there are many UAVs swarming and it is trying to detect, like, the UAVs are actually flying in at a certain speed.
Yeah. So you will. The increasing band.
This is some.
Yeah. So that's about the sensor. If you have any questions offline, also you can just send me an email.
So I thank Professor Linga Reddy for giving the talk on radar-based systems for cyber physical systems. So thank you very much, Professor Linga Reddy. So on behalf of IIT and on behalf of the workshop organizers, I would like to present a small memento. Thank you.
Yeah.
think mic is just this. So good afternoon, everyone. Oh, you want to introduce?
Yes.
అప్డేటెడ్ ఇచ్చాను సార్ పాతది అప్డేటెడ్ ఇచ్చాను సార్ Very good afternoon, everyone. It's my privilege to introduce our Professor C. Krishna Mohan, sir. So he's currently a professor in the Department of Computer Science and Engineering and Dean of Public and Corporate Solutions at the Indian Institute of Technology, Hyderabad, India. He has been with IITH since 2009. He was also the head of the Department of Computer Science and Engineering, IIT Hyderabad from May 2010 till October 2014. Before joining IITH, he was a senior faculty member at the National Institute of Technology, Karnataka, Surathkal. He received his MTech from NIT K, Surathkal, and PhD from IIT Madras. Professor Krishna Mohan Garu heads Visual Learning and Intelligence Lab at IITH, working in the research areas of video content analysis, computer vision, machine learning, deep learning. He is a recipient of Excellent in Teaching Award in recognition of distinguished teaching in the year 2018 at IIT Hyderabad. He has published more than 90 papers in peer-reviewed international journals and conferences proceedings. He has guided several PhDs, masters, and undergraduate students. He has successfully carried out several projects with industry, government agencies, and academia. He serves as a reviewer for several reputed international conferences and IEEE journals and is a senior member of IEEE, member of ACM, AAAI, member, life member of ISTE, fellow of IEI, IETE, and TAS. I heartily welcome sir for taking over the session today. Thank you.
Thank you, Divya. Yes. So today I less. So ఇది పనిచేస్తుంది Okay. So today I give brief presentation on learning social interactions in surveillance videos. Okay, so before actual presentation, I would like to acknowledge all my students for contributing this work what I'm going to present. Okay, so learning social interactions in a traffic scenario involves human interactions and also the human object interactions like navigation of autonomous vehicles and so on. Okay, for example, you can see that ఏమవుతుంది రఘు ఓకే
ప్లే అక్కడ క్లిక్ చేయాలి సార్ మీరు.
some problem.
ఏం లేదు కానీ దీంట్లో అలా వస్తుంది. వస్తుంది అది పీపీటీలో అలా ఉంది సార్.
లేదు I gave several places this presentation.
ఇప్పుడు వస్తుంది.
Yeah. So as you can see, like, learning social interactions in a traffic scenario, you need like, object to object interaction, object to subject interaction, and so on. Okay, there are many various interactions happen in traffic scenarios. So you can also see like, one of the applications, navigation in autonomous vehicle, where these interactions are important. Okay. So pedestrians in a traffic scenes, follow different trajectories to avoid obstacles. Okay, and autonomous vehicle navigation, such as a scene, okay, should be able to foresee the future positions. Okay, that means forecasting. Okay, forecasting the future predictions of the pedestrians. Okay, because it is important for autonomous navigation. Okay. Yeah, and also like modeling social conventions in real world. For example, some humans have the innate ability to read one another. Okay, so when people walk in a crowded public space, such as sidewalk, or airport terminal or a shopping mall. Okay, so they obey generally a large number of unwritten common sense rules and comply with social conventions. Okay, so for instance, they consider where to move next. Okay, they respect personal space and yield the right paths and so on. Okay, so these are important for to model these kind of interactions. Okay. So predicting the prediction motion of human targets, okay, while taking into account such common sense behavior is extremely challenging problem. Okay, you can see that the modeling higher level semantic interactions among the various agents helps in better scene understanding, predicting future behavior trajectories, and anomaly activity detection. Okay. So you can see that different kinds of interactions, like subject to subject interaction, subject to object interaction, and object to object interactions. Okay. So basically, the research in video surveillance and environment monitoring gives us the recent trends in bringing the analysis of the scenes at very higher levels, shifting attention from the traditional agent sensing to, like, for example, agent sensing. You can see that vehicle sensing, vehicle detection, vehicle tracking, and then object detection. And for example, in object detection also, helmetless driver detections and helmet detections, particular fine grain detections and so on. Okay, and then vehicle tracking the vehicles so that you can see the anomalous behavior of the vehicle, or generate some alerts to the police control room and so on. Okay, so we shift this traditional agent sensing to semantic interpretation of events, such as you can see that first application where a person in the actual scene is not there. Suddenly he comes on a bike, and then he snatches the chain of the lady. Okay, so, and also the second applications, you can see that these data is collected by the using the drone at Ahmedabad, I think which junction, Paldi junction. Okay, it's a 4-lane junction. Okay, so we wanted to detect the accident prone areas. Okay, based on the traffic predictions and so on. Okay, and then the other one we have worked on is this accident detection. Okay, so you can see that this is the real data collected from the Hyderabad city traffic. Okay, and some of these accidents. Okay, so we try to understand these social interactions in order to do various kinds of tasks in surveillance video analytics. Okay. So coming to the subject to subject interaction. So one application, as I told you, is the snatch theft detection in unconstrained surveillance videos. Okay, it's not constrained; it's unconstrained surveillance and real time. You can see the various kinds of the event, same event, but in so many different ways it happens. So there is no exact definition of what is snatch theft. It's very difficult to define, okay? And you don't have, for example, if you want to model these kind of interactions, you need to have, large amount of, these examples, okay? But you don't have, you have very limited data of these kind of accidents happening, okay? So you have to detect some unsupervised way of, doing the things rather than supervised way of doing the things, because you don't have many labeled examples. Okay, so you can see that first example, the person starts talking to, that lady, and suddenly snatches her purse. Okay, and similarly, you can see that other event, suddenly, appears in the frame. See, camera is from this angle. Okay, so and lady walking, corner of the street, and suddenly, he comes on the bikes and snatches away the events. And similarly, you can see the other events here. Okay, so each one is unique in nature. Okay, and then the way you capture, okay, also poses the challenge. Okay, so for example, you have poor resolution, then occlusions, illumination problems. Okay, so there are varieties of problems along with the diversity of the snatching event itself. Okay, so that's why I said, like, there is no strict definition of what is a snatching incident. Okay, a snatching event. Okay, so and also, like, none of the testing scenarios are same as the training scenarios. Okay, so that is the biggest problem in identifying these snatch theft detection. Okay, so, and as I told you, not enough labeled data, so you need to do some unsupervised way of learning things. And also the atomic events cannot be identified clearly in real snatch scenes compared to stage snatch theft. Okay. So existing representations like, general Fisher vector, classical Fisher vector representation, where you have low-level features, are mapped to some high-level representations, like, using some clustering and bag of words and so on. Okay, so the main problem with these representation is, again, very high-dimensional data you have, and then you only mainly capture the global characteristics, but unable to find the local similarities, which are important for these kind of surveillance, applications. Okay, and the class-specific, class-specific models perform better than class-independent models. So the class specifics are problematic to train unbalanced classes. Okay, so the problem is also another problem posed here is the unbalanced classes. Okay. So, and also coming to the recent approaches based on deep learning methods. Okay, also, like you can see that, a high level representation directly from the raw data. Okay, and for that you go on applying nonlinear transformations. Okay, both in spatial and temporal domain, and then extract that information and try to, provide the representations, okay, for effective snatching event detection. Okay, again, issue remains the same, that is the representation is high dimensional. Okay, you can see in this case it is 4096 dimension. Okay, and again, all deep learning models require the labeled data. Okay, that means annotations are needed. Okay, so, and also large amount of data. Okay, so the problem is we have very limited amount of examples of snatching events. So modeling becomes difficult, and modeling becomes much more challenging with these kind of problems. Distance from the camera, poor resolution, illumination problems, occlusions. Okay, and other problems is like, diversity of, snatching. There is no unique way of snatching, snatching event. Okay, that you can see the diversity. Okay, you can see, previously you can see the varieties of events, same event, but happening in a varieties of ways. Okay, and similarly here also. Okay. So it's quite challenging to model these kinds of interactions. Okay, we started looking at this problem from the perspective of representation learning. Okay, so where we can try to tackle these kind of issues and come up with a better robust methods in identifying the events. So we try to learn the abstract and meaningful representation from low level, like videos or speech signals or any kind of this one. Okay, capture the distribution of the hidden explanatory factors for the observed inputs. Okay, so human interaction. So we consider human interaction as a snatch theft detection. Okay, sorry, yeah. So what we try to do is, for example, some actions like I've taken examples of some sports events. Okay, so you can observe that suppose if there's a boxing action. Okay, so we try to consider the human actions as a sequence of atomic attribute some atomic attributes. Okay, we try to define each attribute. For example, in boxing action, one can define attributes like right hand punching forward, right hand retracting, similarly left hand punching forward, left hand retracting, and so on. Okay, so we try to define these kinds of attributes. Okay, so that the actions can share all kinds of these attributes in though some actions may not have all the attributes. Once you have put together all the attributes in one basket, okay, so any action can share the attributes required for a particular action. Okay, that is the concept based on which we came up with this representation learning. Okay, so for example, if you look at the first figure, where you have two actions. One is the cricket bowling action, and then tennis serve action. Both look similar. Okay, even for humans they look similar, but you can imagine for a machine. Okay, so the reason is that different actions have similar attributes in terms of motion and appearance. Okay, so we need to model these kind of actions. And also, if we can define the atomic attributes, then it becomes easy for all actions to share these kind of attributes. Okay, and similarly, you can see the other second figure. One is tennis shot playing action. Other one is volleyball shot action. They look similar in terms of motion and appearance. Okay, so our thinking was like, can we exploit this local interaction similarity implicitly? Okay, that is the basis on which we started working on it. Okay, so so that we don't need explicit annotations. That means we wanted to do unsupervised way. Why unsupervised way? One is that we have very limited data, and the second problem is that diversity of the same action. Okay, so you cannot exactly define how a snatching event happens, because it happens in varieties of ways. Okay, so for that purpose, we try to define these atomic attributes, and this sequence of atomic attributes define the action, particular action, like snatching event action. Okay, and so on. Okay, so this is the basis on which we started working on it, and it proved to be worth exploring this. Okay, so what we try to do is model the attributes of all actions using large Gaussian mixture model. Okay, you take one super Gaussian mixture model and put all action all attributes of all actions. Okay, for each action you define attributes. Okay, and all these attributes are modeled using Gaussian mixture model. Okay, that's why we call universal interaction model. Okay, and then what we do is we do some sort of unsupervised factor analysis to extract important attributes for each action. Okay, and we call that as an action vector representation. Okay, and then this action vector are used to modeling the complex activities like snatch theft action. Okay, so you can see you can observe that you have clips of all actions, okay, all action clips. If there are 100 classes, you have, all the 100 classes here, okay. And then from that, you do the some sort of expectation maximization and try to come up with, the universal interaction model. That's what I described just now. And then given a particular action, and then to try to do map adaptation, okay, maximum a posterior adaptation, okay. And then from that, you get again, problem remains same because you get high dimensional data, okay. So we come up with a unsupervised factor analysis, okay, to bring the high dimension to low dimension, so that we have efficient representation in of this snatch theft detection event, okay. So you can observe that, you can see that the snatch theft, events are only 35 examples you have, okay. And total interactions are 850, but the number of snatch events are very less. So it's very difficult to model, because of the limited amount of data you have, okay, it becomes very challenging to model, especially deep learning approaches fail, okay. They don't effectively do it, okay. So we, we explored first deep learning approaches, but later on top of it, like still we had same problem of high dimension, and it was not able to, it was not robust enough, okay. So we went for this representation learning, and you can see that, we could perform better, and robust model we could develop. And this has been implemented in our Hyderabad City Traffic Police, system, okay. This model has been tested and installed. These are some demos, of what we have. You can see the bounding boxes, and then so when snatching instant happens, like you can see like how it is able to detect, and we are able to detect in real time, and in 10 seconds you generate alerts to the police control room. So we are able to do, because we have done in unsupervised way, and we are able to generate alerts in a very short time, that is 10 seconds, to the police control room, okay. And we have also done a user interface, okay, so that this police people can see from which camera, okay, which place this event has happened, okay, and which time, all that is recorded, okay. So this has been appreciated by Hyderabad City Traffic Police Commissioner. So earlier I discussed about the subject to subject interaction. Okay, now coming to the subject to object interactions. Okay, so this is the data we collected from the Ahmedabad city traffic using drones. Okay, it's a drone aerial data. Okay, so detection of collision prone vehicle behavior at intersections using Siamese interaction LSTM. Okay, so basically, we try to do spatial localization of collision prone behavior at intersections. Okay, so where we try to, which is the safe, and safe, like we try to divide into 3 states: safe, unsafe, and unsafe. That is interaction of trajectories for vehicle I, and interaction trajectories for vehicle J, and so on. For each vehicle, we try to provide, basically we try to do the trajectory predictions of each vehicle. Okay. So we try to come up, provide, for each vehicle, okay, we come up with, LSTMs, and then try to use some triplet loss, okay, and then we try to predict the, trajectories. So we call it as a SkyEye data set, which we have created. So where we try to indicate the vehicle trajectory in the next step, time instant, okay. So where red indicates the unsafe interaction, so that means there is a collision prone area. Okay. You can see that collision prone areas in this. Okay. So the last one is that object to object interaction, where we try to anticipate highway traffic incidents from surveillance videos. So this is the, like, our highway data collected from our highway. in this national highway, going across our in front of our IIT. Okay, that is not IIT, but this is the highway in front of IIT. So what we try to do is any noticeable situation in which two or more vehicles meet each other in the same space and time. So with their movements remain unchanged. Okay. So some of the accident scenes, like we try to divide into different states, like incident. That means when the accident, because we are trying to anticipate whether accident is going to happen or not. So we call it incident. That means before this one, and at the time of accident, and then post accident. Okay. So the approach we followed is this. We try to detect each vehicle. And also like using some surrogative measures, we try to say that whether it is a normal accident prone or normal accident prone and so on. So we, basically we try to predict for next time instant how the vehicle is moving. Okay, so that you can predict the vehicle is going in the going to meet with an accident or not. Okay. So we try to do the sequence of prediction tasks by and we come up with predict the future tracklets, okay, of a vehicle based on their past spatial positions, and also we adopt state of the art detection and tracking methods to obtain spatial coordinates of all the vehicles in a scene at every time step. Because see, every vehicle moves with different velocities, okay, and acceleration, and follows different motion patterns. Okay, so it is important that we try to accurately do the prediction part. Okay, I think I'll skip all this. Okay, these are some of the surrogative measures which and I will try to share this material with the participants. You can go through this, time to collision, gap time, and encroachment time, and so on. Okay. So this is the data set. Standard data sets and our data set also. These are the some qualitative. I don't know whether they are able to play. No. Yeah, these are some of the results we have. Quantitative results and qualitative results. So other works we have been working on is image and video captioning, and then fine grained action recognition. Okay, and so I think it's time like for the yeah. So it's time for the break, and already exceeded the time. So I'll wind up. So, but I can take of the this one, any questions or interaction, and also if you need more information, you can always write to me, so that we'll be able to this one. And I acknowledge all my students for doing the work. So thank you very much.
Okay. So on behalf of the committee, small.
So I thank him, he thanks me. So I give him, he gives me. I read his biodata, he reads my biodata.
So we take a tea break now. Snacks and tea are available. I think we take a 15 minutes break, then we come back.
Yeah, because we are already half an hour late.
So there's a tea break. There are snacks and tea will be available. So is the same place?
Yeah, here only.
This will be here only. Okay, right. So we come back in within 15 minutes. Within 15 minutes.
Yeah.
Yeah.
Hello,
Jamie? ఇందులోనా తీసిపెట్టు తీసి చార్జింగ్ ఎక్కలేను కలిగి
ఛార్జింగ్ ఎక్కలేదు.
ఇది ఛార్జింగ్ ఎక్కడ తెలుస్తుంది
ఉంది కదా, పెట్టేసావు కదా.
పెట్టాను ఇక్కడ
ఛార్జింగ్ అవుతుంది. ఇది ఇది అది అది తీసి దీంట్లో పెట్టాడు. దీంట్లో ఇది పెట్టాడు. ఇది ఇక్కడ ఉంటుంది. ఛార్జింగ్ అవుతుంది అన్నది ఇది. డూప్లికేటే కదా ఉంది. వచ్చింది.
I thought if you might not be me, we might not have. That's what I thought. So then I went to position. You should tell me. I tried to get something. Come on. It was about to start. Was somebody was telling you it is getting good food there. It's nice conference. Even if they were just really letting me learn get to eat good food always. Wow. And you know what? You understand what I want? And it's step side. Okay. Right?
Yeah.
What you have been
I mean, this one. This, I saw that. Big company. There are secrets. Secret things. But no, he won't make the missing.
Who's taking this?
Yeah, it was.
Okay.
Problematic smart.
Who's taking this?
So basically, I didn't know what was that one. We had a thing that's like that is like that.
But it is start.
It's like class conditions. So what I did, so everything picked up like single sort of but I didn't know the real task to me. So I did all the survey, sending the survey. So I was doing the survey like that. Then that's all I did. That made the very impressive. The only God out there for the 2 days. That is like this chapter. So they like years to come up with that design. But I did one problem. Doesn't have to be like general. Yeah, does that. But you should take on real value. It's like a major full framework. Because then you verify videos stressing about they wanted to keep one link.
Yeah.
So it's more with the main science.
Scientifically, because there are certain limitations, and they don't know the street photography and all with that, right? So they're just keeping it for a time, and it's like running and like the players and all those things.
Recording isn't it?
I don't think you like art or like updated. But if you make it with all or something, but one should be skill production. But I was someone to take it. This something
Good evening, everyone. Very good evening to one and all. I take privilege in introducing a Professor M.B. Srinivas Mandalika. And M.B. Srinivas Mandalika has been a professor of electronics and communication engineering at BITS Pilani for about 14 years now. He is currently with Dubai campus of BITS Pilani and is a university-wide Dean of Graduate Studies and Research. His research interests include advanced memory technologies, VLSI arithmetic, and machine learning to address societal problems. We heartily welcome you, sir, for taking over the session.
So you may reserve the claps to the end, if at all you think the lecture deserves that. So yeah, thank you very much for the opportunity. Very interesting autumn. This is my first visit to IT campus, although we've been just about an hour away or so. Of course, I know some people here already. Dr. Zafar, anybody from ECE here? Maybe not. So Dr. Zafar Ali Khan, right? Zafar Ali Khan was my colleague when I was at IIIT in Gachibowli. And of course, people like Asudev Datta and Amit Achar, these are all the people I knew for a while. And of course, I need to tell you confidentially, because the other gentleman doesn't know this. The current director and I were kind of contemporaries at IISc, doing PhD. Although I know him, but he doesn't know me. Obviously, I don't deserve any such, knowledge of me with him. Okay, very good. So thanks so much for the opportunity. So Dr. Linga Reddy and I, we've been working together for a while through Indo-Norway collaboration. And we are actually doing several things. So this is something that came up more recently because so we have this Kaloji Horticulture University very close to our campus. So we happened to sign an MOU about 3-4 months ago to bring in CPS for improving the shelf life of agriculture and horticulture produce. It's a huge opportunity for many people. So one of the reasons why I wanted to talk about this, not much about what we've been doing. Of course, one reason is that he's the boss, he's the expert, and he must have already spoken about it. So for me to talk about it doesn't really make sense. I may be exposing only my ignorance. The second thing is that, again, this is a huge opportunity for research. So there may be young faculty here, but all of you look to me like students. So, as students, you have a great opportunity both to contribute as well as possibly go for your own startups. It's going to be a huge business. And the third thing, which is more important than the first two for me, is that, since morning today, as well as tomorrow, day after, you are going to listen to highly mathematics and theory intensive lectures, which puts me on a little weak wicket. So I want to present something that's very, very ground to earth, non-mathematical, amounts to just reading out from the slides so that I can be very confident in my lecture. Okay, so kindly pardon me if you don't find any mathematics here, because coming from IIT, you guys must be very mathematically oriented, which should be the case, of course, if you are an academician. But then the purpose of this is the opportunities in this agriculture and horticulture sector, one thing. The second thing is the big concern about the climate change. And then, the one of the slides is going to tell you how much we are currently losing in terms of very inefficient supply chain in this country for agriculture and horticulture. And then the urgency to develop solutions, and that can also be realized at the ground level. Not a kind of rocket science. Anybody can do this because the technologies exist. So the purpose of this talk is more to expose you to this field to the extent I know, and then possibly look for opportunities yourself, because there are agriculture, horticulture university, they have extensions around this place, and you could talk to them, and I can support you whenever you need that. Okay. So this is cyber physical system for monitoring agricultural produce, and CPS is being used in a very, very loose sense, in that you have sensors, you have IoT, you have connectivity, and then you have predictive analytics, and you can combine all these together to form a kind of a CPS, right? So that's a kind of, so the framework as it applies to this domain is the purpose. Okay, so that this introduction should make you aware of what it is and what it is all about, and possibly define your own career going forward, at least part of your career. So that is the title, and then there are multiple authors here. Vandana was a graduate student with BITS, and then she's currently doing her master's in US. Then Jagdish and I, we are colleagues in BITS planning. So some of this work was done by Vandana, the practical work, which I'm going to show you later. And Jagdish was, helping to put together some of those technical slides. And Dr. Shankar Swami is from Horticulture University, and he is the guy who is the domain experts. So one provided the domain slides, the other provided the technical slides. Because of my seniority, I could put them together and build a small story around that and present to you. Ideally, they should be talking. I'm not the right person, but then, that's how the world runs. The truly deserving people very rarely get the recognition within these four walls. Okay, don't quote me anywhere. Okay, of course, all kinds of things happen. So I believe in karma. So not when I was young like you, but after graying my hair. So these things you will learn as you go along. Okay, so that's a kind of a brief, uninteresting introduction to eat away a few minutes, so that Dr. Linga Reddy, when he writes a report, says, "Oh, Srinivas gave 1 hour lecture, 40-minute lecture, whatever." Very good. Okay, thanks for the patience. Okay, so let us come to the reality now. If you talk about the agriculture and horticulture domain, you all know what is GDP. Okay, so Indian GDP currently about $2.53 trillion kind of thing. And compared to that, the Chinese are around $14-15 trillion. Americans are $22-23 trillion. That's a kind of a gap. Okay. And the politician, as usual, oh, India is going to be a $5 trillion in 2025, $10 trillion 2030. You don't have to necessarily believe. Okay. As scientists, as engineers, as researchers, as people who have concern for other people and concern for the society and the country, we need to be looking at the real numbers. So about 1/3 of the Indian GDP comes from the agriculture, okay, which is big. And it has a potential to increase significantly, provided you have a government which is concerned about the people rather than elections. Okay? So sometimes I talk like an NGO, please pardon me, because at this age I have really big concerns. Okay, so I'm trying to see the interface between technology and people's lives and see how best we could contribute to improving the lifestyle of the people. Okay, so about 6%. So considering that 30%, 1/3 of 2.53, let's say $1 trillion, 6% of that is still a significant, something like $60 billion kind of thing comes from horticulture kind of thing. Okay. And the problem with this is that you need to, consume as you generate, like electric power, Electric power, typically, you don't have storage systems. Of course, Elon Musk talking about the battery storage, set up a 500 megawatt hour kind of thing. All those things happen, but very expensive. A poor country like India cannot really afford setting up a storage for electricity, right? So therefore, you need to consume as you produce. But then the horticulture produce, like fruits and vegetables, typically come under horticulture. So they have a very limited shelf life. Okay. So one of the examples was being given by the horticulture guy to me is that the coriander predominantly produced in southern states like Tamil Nadu and transported to northern states because they don't grow in Maharashtra and Gujarat. But then its shelf life is less than 1 day. So by the time they transport, the whole thing goes bad, So the thing is, they were asking us, can we have an online monitoring system that will help us to monitor and therefore take corrective steps so that it gets preserved, the shelf life gets preserved till reach at that place. So obviously we have our technologies to, because they have no idea of these technologies. Okay? So they have limited shelf life. During storage or transportation, they lose their thing. Okay? Of course, revenue loss I'm going to talk about. And then, we don't beat China any domain other than this domain. So therefore, we are going to exceed our population, the Chinese population, by about that time. Okay, and you need to feed so many people. And as such, you are not producing enough food to feed. On top of that, you are experiencing almost 40–50% losses in the food. What is the point? Okay. So this slide, you can see, right? So if you typically look at the kind of mechanism in the entire growth and, of these horticulture things, and then the relevant parameters, you start from a farm, then go to supplier, packaging, transportation, distribution centers, retail, finally it reaches out the consumer, right? But then if you look at a leafy vegetable kind of thing, it loses its shelf life mainly because of the condensation, mass loss, conduction, respiration. So all these things, normally we don't pay attention. We just go to the market and then try to look for fresh vegetables. But then, they lose their significant, nutritional or the other content in the process, right? So therefore, ideally, you would like to preserve that. But then before preserving, you also want to see which are the parameters that correlate well with some of those fundamental parameters like temperature, mass loss, quality, the remaining life, thermal, pest infestation, those things, right? So therefore, if you are, because in a CPS, typically at the lowest level, you have the sensors and IoT kind of thing. So if you can identify what are the right sensors that you want to use, and then collect the sensor data, and then you make a physics-based modeling that will help you to come out with a model that relates all these parameters and relating that get related to a function that is a function of the health of the vegetable or whatever that you're going to do. And then do a predictive analysis, and based on that, you derive actionable metrics which can help you to preserve the produce till it reaches the consumer. Okay? So overall, this is what you want to do, but then some of these universities are horticulture universities, and some of the companies involved try to do to some extent, but still they are limited by the multi-dimensional nature of the problem, as well as the massive data that you need to analyze before you can come out with a meaningful model that can predict the shelf life or whatever. Okay, so this is basically not an easy problem. So why do they go, rotten or whatever? They're all perishable. Those are the things. Because one reason is that you are not able to monitor and maintain the critical ambient characteristics, which are very important, right? So so one of the experiments that I'm going to show you later on is that to simulate the transportation, the produce during the transportation, and try to measure certain parameters. And as I said, the kind of loss that you are looking at is 93,000 crores every year because of the thing. Okay, and then and this is not Indian phenomena alone; it is all across. and typically about 2 billion people go hungry. You ask yourself, if you are hungry for one day, you cannot really sustain, right? And imagine these people go hungry almost on a day-to-day basis. So the point is that if you have a mechanism to monitor and then quantify and predict, possibly you can contribute to the wastage coming down significantly, and therefore you are able to save, so much. In this country, as you know, there is so much wastage on every front. So one of the main reasons for all this is the kind of supply chain that you have. So if you are a mechanical engineer, you will know what is a supply chain. It spans further because there are more suppliers and partners, and therefore, unless there is a standardized mechanism of putting a framework together, it's going to be very difficult to eliminate this spoiling of this produce. And this is a major problem, okay? And therefore, it leads to instability and prices. The farmers will not get the remunerative prices, rural impoverishment, all these things. So these are all, kind of, fundamentally it is there, and these are all the consequences. So I said supply chain. So what is the supply chain now? So you have farmers on the one end growing, and then of course you have agents, you have auctioneers who buy from the farmer and then give it to wholesalers, and then you have retail vendors and before reaching to the customer. Alternatively, you have a producer, they form an organization, and then sell retail. So this is the kind of supply chain through which this produce goes through, and then things can happen. Things can go wrong anywhere here unless everybody involved. So why should farmer, as it is fresh, he will sell it off. He will not bother about monitoring. Agents and auctioneers, they can tell you any number of lies to say that everything is perfect. They don't care. Wholesalers, perhaps they will have a warehouse to store, but they will not monitor. And then cart vendors is also not bothered, okay, as long as there is a consumer to buy. So if you go to a push cart here, there will be a variety of apples, and he knows there is one customer for every type of fruit. And by the time he's done with the business in the evening, the cart is empty. Okay, so therefore, nobody apparently is really bothered about preserving this produce. So if you look at how the kind of commissions people get as you move from the farmer to the consumer, so the guy like an agent who is a consolidator may get about 2 to 5%. Okay, so it appreciates from there. Then the trader, 7% official, but then it can go as high as 40% or so. So trader to agent, 10%, wholesaler. So it kind of cost keeps getting added as it moves from the farmer to the consumer, and we are all helpless. Okay, so the best thing is you grow your own vegetables and fruits, ideally, but then you cannot do everything. You need to have proper place. Terrace garden people talk about, perhaps you can try. But then I see huge towers, residential towers in IIT. So one terrace place is fought for by 20-25 families sitting below. So perhaps terrace garden is not possibility. But then again, so the point is that as consumers, we are at a loss. And if you have a technology background, perhaps we can step in and see how to, in our own interest, can we develop technologies? Okay. So why do you want to do this? Safe supply chains, because safe means that you want produce to be as fresh as it was when you moved from the farm to the house, okay? Because you want food and nutrition security, environmental sustainability, production costs, and prices are always on the rise, contributing to inflation. So these are all kind of built up. If you suddenly look at inflation, so yesterday I think World Bank or somebody said in the beginning of the year, India growth rate was 8.2%. Then they brought it down to 7% in the middle of the year. Now they say it is going to be around 6%. So all these growth rates, of course, we may not worry about the growth rate. Ultimately, I am worried about my salary. You are worried about your fellowship. And they will never go up because all the expenses, just keep disappearing in the supply chain. Okay, so all these have implications to what is happening in different fronts in agriculture industry. And this is one of the most inefficient country to live in. People don't have that, that culture of efficiency. So this is where I thought I'll bring in that cyber physical to be consistent with the collaborative project that we are doing. So how to bring in the technology to preserve this horticulture produce. So typically, everybody knows you start with sensors, then you have a network of sensors through IoT, and then push the data, collect the data, push to the cloud, and then do a predictive analytics on top of that. Okay, but it is easier said than done because that data could go corrupt anywhere. Okay, so you need to have a lot of interventions in between to make sure that before you deploy predictive analytics, you have clean data that will predict correctly on what's going to happen. Okay, so that should link to the farmers, vendors, so all these people need to be connected through a CPS that could possibly help in continuous monitoring. And it is based on science. It is not simply the data, but you also need to bring in domain knowledge into the predictive models or machine learning model that you are talking about, and then see how they can be combined to make right predictions, which can then be relayed to the supply chain managers so that you can preserve this. Okay, and eventually it will result in competitive pricing, reduction in inflation, and things become affordable. And that is when you stop worrying about your scholarship or salary kind of thing. Okay, so so that kind of implication is there. So this is something you're all technologists. You have an IoT-based network with monitors, indicators to. So this is where the domain knowledge will come into picture. Okay, so when I say the leafy vegetable has a respiration. Okay, so what is respiration? How do I measure that respiration? What kind of sensors can be deployed to measure that? And then later on, how to quantify, like what is there a threshold level of respiration beyond which I will say it's spoiled. Okay, so this kind of data will come through the sensor, but you need to have a base data which you need to generate in the lab. Okay, that is what we try to do. So one of the experiments I'm going to show you toward the end. Okay, then the data carrier technology needs to be integrated with the whole thing, like Narendra Modi was talking about 5G kind of thing. I don't know what kind of 5G that is. We don't develop the technology, right? Somebody give the technology, we'll just put together and say that India is 5G country. So anyway, better do something rather than not doing anything. So so we need to provide real-time information on the fruits and vegetables, entirely the environment, and then in the process getting kind of spoiled. So things like biological variability and actionable metrics in real time are important for providing the real-time data on the post-harvest produce. So this is something that you are familiar. So because this is where we all kind of. So what you have is that you have a set of sensor nodes which will collect the data locally. And then the whole thing, this master node could be through your solar and then a kind of standalone. And then the data is collected and aggregated and pushed onto where maybe cloud or a separate server that you set up to log in and then keep monitoring the data. Okay. So one thing that may be useful to you who want to kind of attempt this kind of work is the sensory knowledge. Okay, so I'm sure there should be some sensors being developed in this very institute, but there are also commercially available sensors that one could use of. Temperature, you all know, and this could be LoRa enabled kind of thing. And then the freshness. Okay, so there is something called a sensor called fresh tag. Okay, so if you use that, it will give you the time variation of the temperature. Okay, and therefore, with the help of rest of the sensors, you will be able to see if the produce is still fresh or not. Mind you, the produce is actually being transported in storage, air-conditioned storage containers across the country. You don't really know what is happening inside. Okay, So that is where we are currently working on setting up a test bed, okay, having multiple produce, like some of these vegetables and fruits, have these sensors, get the data on a continuous basis, keep interacting with agricultural scientists on what this data really means in terms of the physical status of the produce. And therefore, we are trying to set some thresholds to say, and these thresholds, once you get that knowledge of thresholds, then even in an unknown environment like a refrigerated truck, you can put these sensors and then keep monitoring and detect when something is going to go bad, and then locally take a corrective action also. Okay, so we are also trying to do that. But then the sensory knowledge is very important, sensor calibration, all those things come, in a slide I can explain everything, but the real life, as you know, is much difficult. So the freshness to locate, track, and monitor the physical attributes, and of course, things like pH, moisture, ripeness, spoilage, microbial indicators. These are all, most of us being not from the domain, we will not know these things, but all these things are really important and contributing factors to the losing out the freshness. Okay, so there is a sensor called ripe sense. Okay, so things like methanol, ethanol evolution. That gas evolution can be monitored, quantified, and correlated with the freshness. Okay, so this is another sensor. Of course, there are also calorimetric sensors, which will, the volatile organic acids I was talking about, and the gas sensor for oxygen, carbon dioxide, because these are all again indicators of the freshness, the color change, right? Then microbial spoilage. So microbes can also, so you have optics-based sensors that can be, detect, the sensors could detect the change in color and therefore be able to attribute to the action of the microbes. Then, of course, you have, humidity, temperature, humidity. This is something as the students you do in the lab, right? So capacitive sensors can be used. Then, like what I said, the fresh tag and other monitor mode fresh check, these are all other sensors that will detect any passing up, whatever threshold that you keep, and then warn you about what's happening. So this is again something repetition. So I talked about freshness, temperature, moist. So these are our other sensors that could. So dry lock is something. It's a intervention that one could do. This intervention will help you to remove the condensed moisture, which could actually spoil the thing. So there are sensors to detect. There are also certain intervention mechanisms that will help you to take a local action in trying to, prevent the spoil. Okay. So this is a slightly different picture of what I mentioned earlier. So for example, you can have ethylene or methylene sensors. So these are all kind of local nodes, and then they will pick up the data and then keep pushing to the server, onto the database, and then, then to the cloud if you want, and then individual users will log in. So these are the models that you are very old, these are all familiar to you. So where does this kind of model CPS where does it find its usage? So it could be in crops, agriculture crops, household. People these days talk about, household terrace. What is that? There is a term that is used for the terrace gardens, which are really big ones, not small ones. And then forecasting also, this is useful because you collect the data, carry out research, and predict using predictive analytics. You should be able to forecast when, rains and kind of relate to that. And then monitoring the irrigation of the sports facilities. So once you have the CPS in place, all these things can actually happen. So from here, I just want to show you what my student did in the lab. Again, for people like you, Arduino and those things are very familiar. But this is just a sensor board, which gives you both the analog, digital, and then, it's a moisture sensor, it's familiar to you. And this is the entire module that you get, that kind of V-shaped module, right? So these are some of the details of that, and then anybody can do it. It's not a big deal. Just a few days project that you can do as a small mini project you can do as a part of your course. So what we did in our lab is that automated plant watering system. Normally you have all those pots, right? And then always the concern is that when you go out, when you're traveling, there will be nobody to water your plants, right? So we developed a small system. I forgot to copy the video, but I want to show you the video. So you can have the sensor, the hardware board and everything, and then on a certain preset time, you can actually water. That's one way. The second way is to keep humidity sensor in your gamlas and then keep monitoring the, that's a moisture sensor, right? So using those levels, you can actually decide. Again, you develop certain base data, and then from there you calculate the thresholds and decide when the watering needs to be done. So this was done by students in the lab. So one project that we did was, of course, it took about 2-3 months because there's a lot of hard work involved. We wanted to know whether we could monitor when the tomatoes will get spoiled. Okay. So what we did was we initially spent a week only looking at the tomatoes. Okay. So day 1, day 3, day 5, and day 7. So you could actually see that bit of discoloration happens. And of course, softness and all by touch you will know, but you need to know how to measure that. And then some fungal kind of growth can also happen. Okay. So
Water is taken out, the stem is not taken out, that stem.
okay.
The lifetime will be much longer.
Okay, if you keep the stem. Okay, okay. Yeah, see, this is the kind of domain knowledge that we want, Yeah, but anyway, we are not telling the world that, okay, do this way, your tomato will be fresh. No, this is just, but then this is a very next experiment, we'll make sure. Okay, so manually, we try to observe this. And then after placing the sensors, we wanted to see how some of these could actually be reflected in the state of the fruit. One thing. Second thing is we wanted, as I said, when you are transporting fruits and vegetables across the country, you put in a air-conditioned storage truck and they will be packed in various boxes and kept, right? So locally they make it getting degraded. So in the lab, we try to simulate or we try to emulate a box like that, okay, through controlled and air-conditioned chamber. And from there, so we try to replicate the ground situation as much as possible. And that's what I'm going to show you. Okay, so the purpose is to detect the quality using cameras. You want to see visually because human eye you have seen and you have seen some changes. So you want to place a camera and then see if you can do a bit of image processing on the color, texture kind of variation and see whether you could see a change in the quality. Then, of course, you pick up the data and then analyze. Okay. So we have a camera, we had humidity sensor, and then we had other sensors also. And then, get the data, send to a processor, and the processor in this case was the laptop, okay, whatever the server class processor that was there. And we use that to analyze that data. Okay, so what we did is interesting actually. This was done by a girl student, This is a refrigerator. She bought the refrigerator by herself. Okay, and she kept it in her hostel room. Okay, and she manipulated the entire refrigerator to make sure that the sensors and everything is pushed in. I'll show you. Okay, and she actually created a transparent window on this, and then she mounted a camera externally. Okay, so to observe the images, right? Then this is a set of sensors that are actually used, and you could actually see, again, you see the back of the, so what she did was, she removed the back plane of the refrigerator and then made all those holes and created the electric sockets to plug in her sensors over there behind the refrigerator. Then this is the complete hardware board for analyzing. It has your power supply, your set of sensors, and a processor board. Okay, so everything integrated on a board, and this will monitor your sensory data that is coming from inside, and along with the camera, the output that is being given by the camera. So what you see here, that black one behind is the refrigerator. Okay, and then the sensory data is coming through a cable after making holes into the refrigerator, and through cable, all the sensory inputs are being brought into this hardware setup. Okay, this is the handle of the fridge. And this is how the whole thing looks like. Okay, so on the left side, we have a refrigerator that is modified to have a camera inside, and then the sensory inputs coming out, sensory outputs coming out, and the entire hardware is actually fixed to the refrigerator. And then she developed software on this to monitor and the GUI to display the data, and therefore the status of the fruits or whatever, tomatoes in this case. Okay. So this actually represents the box that I was talking about in a refrigerator truck, so that once you set up a base experiment like this, collect the data, validate them through the experts, then next step is to go to scale it up and then try to see whether the same thing would work in transportation also. So she developed a small app. Okay, so she was monitoring the humidity, temperature, and ethanol content and methane content. These are all related to the freshness. Okay, so these values, high humidity, okay, temperature is 21, and these values based on the data provided by the agriculture scientists, this is a fresh food. And after a few days, it started getting rotten. And you can see the humidity, the moisture content of the food was actually going down significantly. Temperature, of course, it's still a controlled refrigerator, right? But ethanol, the emission, ethanol gas came out significantly. Methane was only a small variation again. So you had 139 ethanol versus 282, methane 4 versus methane 5. So what you find typically significantly here is the humidity and ethanol have changed significantly, indicating that it's actually getting kind of rotten. And this was also confirmed by the horticulturists. Okay, so this is a small experiment, but then we want to now scale up and then collect the data on a bigger scale, and then start using some of the predictive analytics on the data to be able to forecast. I think that's the last one. So, so if there are any questions, and I know it is more like a story, not much of a technical content, but then, it is equally challenging. Once you get into that, you will know it's not so easy. But then I thought I'll introduce a topic that perhaps most of you are not very familiar with. Okay. Sorry. I just wanted to show you one more. Wait. So just to excite you with a bit of technical thing, which of course is also, I feel, more comfortable with. Which drive is my E? Oh, USB, okay. Okay, so what I could not show you today is that we are parallelly designing and fabricating a mini drone. The purpose of the mini drone is to, it will be fitted with a camera. So it will locally fly in the farm and then try to look for signs of pest attack. And then, identify which are those. And later on, we are going to add one more thing where we will pump in the pesticide locally so that you don't do it for the entire farm, but locally. That's one thing that we are doing. The other thing we have designed a rudimentary is we are now building a smart artificial bird. Okay, so it's a mechanical bird, but eventually mechanical, it is not autonomous, but eventually we want to make it an autonomous bird, and we will also teach it how to fly. So it will learn how to fly. But what I'm going to show you is a very, very rudimentary video. So this is, a bird-like thing. Right now, it is a kind of tethered, but I'll show you once again. Right now, it is tethered, but eventually it becomes, So we are just trying to see the flapping mechanism. It seemed to have worked. But then eventually we will scale it up, and it's going to take some time, but we are sure it will work. I'll just show you one last time. So you can see the tether, but we are just checking the flapping thing. Okay, the drone also, the micro drone also we are designing. It is in some stage, but I don't have the video right now. But so all this targeted to the agriculture farms, Okay, so yeah. So you don't want to ask any questions, or you don't have to ask questions related to this. You can ask when is Salman Khan's next movie. I'll be able to answer. Okay, very good. It's not easy to sit through this kind of lectures. I know that too in the last hour. But thanks so much for your patience.
So small
Okay. So because I said environmental things, he gave me this, So this contributes to global warming, Thank you.
Okay,
Yeah.
then so we basically conclude today. So we basically start again tomorrow from 9 o'clock. So thank you everyone for joining today, and we have tomorrow very interesting topics from diverse machine learning areas. Also on Sunday, also we have the various topics covering the wireless communications and the medical imaging as well. So thank you everyone. So try to join tomorrow at 9 a.m. Sharp, and we do have the refreshments and the lunch is covered. So when I say the lunch break, so do not go outside.
9 or 9:30?
9. 9.
Please inform all the registered participants, particularly our by 8:30, not 9. 9 for others, not for,
Yeah. All the local students, so they should be here by 8:30. So we usually have the right. So we usually have the refreshments at 8:30. Then we start. Yeah, right. We start at 9, but so try to be here by 8:30. Okay. So once again, so thank you all. So we close the session today, and we start tomorrow at 9 a.m.